Hello everyone, welcome back to the next session of the metallurgy. In the last session, we dealt with how to oxidize the sulfide ore to the oxide ore. And we have already learned what is the requirement to oxidize the sulfide ore to an oxide ore. Yes, thermodynamics gave a proper evidence that I can able to extract the metal which I am going to remove from the impurity if it is converted into an oxide ore. That is why we have found what are the ways to convert the sulfide ore into an oxide ore. Yes, we have undergone a process called roasting through which the metal, the ore which is heated with an excess of an oxygen. Right. If we heat it with an excess of an oxygen, the sulfide ore will be converted into an oxide ore with the evolution of the sulfur dioxide. We have witnessed it in the last class itself. Then, followed by the roasting, we have also undergone a process called calcination. Yes, if the ore has carbonate with it, or if the ore has water of crystallization, we can use the process called calcination. When I say calcination, immediately you have to get in your mind that here in calcination, the ore is heated with a minimum supply of an oxygen, or even in the absence of an oxygen also it can be done. Right. Somehow we have managed to convert the sulfide ore into oxide ore. The next step that we are going to deal with it is reduction of an oxide of metal to a metal. Right. So, in that, the very first reduction of a metal oxide, in order to learn with, you must know certain things. What is that? A metal oxide can be reduced to a metal with the help of a suitable reducing agent like carbon, carbon monoxide, hydrogen, aluminium and other reactive metals. We call it as an alkali metals like sodium. Okay. It is not that I can use all the reducing agent for reducing a particular metal oxide. The choice of the particular reducing agent that I must choose must depend on nature of the metal that I am going to extract. Don't forget it. We have got lots and lots of reducing agent. Irrespective of that, you have to choose the proper reducing agent on the basis of the nature of the metal that we are going to separate from it. Right. Then, the next thing, the first process that we are going to deal with here, smelting. So, through the process called smelting, I am going to remove the oxygen which is present in the metal oxide and I am going to separate a pure form of a metal. Okay, what is the first step that I must do in the melting? First, if a metal oxide has undergone a process called smelting, here the ore would have concentrated earlier itself, which means to the concentrated ore, I am going to add a substance called flux. What is that flux? Flux is the one which helps us to remove the impurities from the ore. We know that the impurities which is present in the ore is called gangue. Right. So, the flux is a chemical substance which is widely used to remove the gangue which is present in the ore itself. Okay. The flux is the one which takes up the gangue and goes as slag. So, thereby I am able to separate the impurity which is existing in the form of a gangue as a slag. One. To the concentrated ore, I told that we will be adding flux. Along with it, you must add a reducing agent. Yes, the reducing agent that you could probably use is carbon, carbon monoxide, aluminium. Okay. We have got all the requirements in order to begin the process. The first thing before undergoing the process we must know here is the mixture from which you are going to able to get the metal should be heated above its melting point. And that heating process should be done in a smelting furnace. Don't forget it. We have to heat here above the melting point of the metal oxide or the metal, right, in a smelting furnace. Okay, now we are ready to heat it. What happens? What actually happening there is, we will be able to understand with the help of an example here. Let me just consider that I am going to separate an iron from its oxide, okay, with the help of a reducing agent carbon monoxide. What will happen there? We'll witness it with the help of a reaction, right. Let me just take Fe2O3, which is existing in the form of a solid. This will be reduced by carbon monoxide, which is existing as a gas. The carbon monoxide which is present here will take up oxygen completely from the oxide. So thereby, which results in the formation of carbon dioxide. 1 mole of a carbon monoxide will take 1 oxygen and go as carbon dioxide. So there are 3 oxygen over here. In order to remove those 3 oxygen, I must take 3 carbon monoxide here. As soon as the carbon monoxide is completely removed as carbon dioxide, the one which is left out here is iron. So 2 moles of Fe will be separated so easily as the carbon dioxide goes out completely as gas. Okay. In the extraction of iron, we will be able to find a gang which is existing as an impurity. The gang that it could possibly have is silica, SiO2. In order to remove this gang, we have already learned that in order to remove the gang, I must add a substance called flux. The flux that we are using here is a basic flux called limestone, which is calcium oxide. This calcium oxide will take up the gang which is existing in the form of a silicon dioxide, and it will go as silicate, which is calcium silicate, CaSiO3. As soon as the slag comes out, we are able to separate it completely. See, the CaO is called as the flux that we are going to add. This SiO2 which I have added is called, this is the gang which is existing as an impurities. This flux along with the gang will go as slag. That's called calcium silicate. This slag is completely removed from it. So this is what the reaction behind the extraction of iron from its oxide. Okay. Now, we look into one more example which will clearly state what is actually happening behind the process called smelting. What are all the apparatus, what are all the equipments, and how the process have been done. Those things will be answered right now. Yes. The next example that we are going to look into it here is the extraction of a copper from copper pyrite. Copper pyrite is an ore of a copper. So its molecular formula is CuFeS2. Okay. What are we doing it? I told you that the ore, before undergoing the process called smelting, it must be concentrated. Okay. To the concentrated ore that I have taken in a reverberatory furnace. Reverberatory furnace is nothing, the one which is completely enclosed with a steel chamber around which bricks will be placed in order to prevent the loss of heat. So that furnace is called as reverberatory furnace. We are going to witness it lively through the video in a minute. In few minutes after the content that has to be dealt. Right. The concentrated ore will be first heated in a reverberatory furnace. Right. Before heating, what I must do is, I must add a flux which is called silica. Right. So after mixing with a flux which is called silica, I am going to heat it in a reverberatory furnace. During heating, what is happening? Right. The very first reaction that we must able to know here is copper pyrite, which is CuFeS2. If it is heated with an excess of an oxygen, here the ore is heated with an excess of an hot air, which is called oxygen, right. If it is heated with an excess of an oxygen, which results in the formation of Cu2S, cupric sulfide, and FeS, ferrous sulfide, with the evolution of a sulfur dioxide. So this is what actually happening there, right. To balance it, let me just mention it as S. Here it is 2, there it is 1, right. So oxygen I need to count. So 2 oxygen is there, here also it is 2, sulfur 4, copper 2, iron 2, everything is balanced, right. Here, which is taken in the form of a solid, here will be depositing as a liquid, here it is as a gas. Oxygen naturally will be as a gas. This is the first step. Then immediately after the ferrous sulfide that has been formed here will undergo oxidation again. If the ferrous sulfide that has been formed undergoes a process called oxidation, which results in the formation of FeO in the liquid state. The sulfur which is present in FeS will take up the oxygen and goes as SO2, sulfur dioxide, as a gas, right. So this is what the reaction is, and this is how the reaction goes. To balance with, let me just make it as 2 here. So iron becomes 2, so here it is 2, sulfur becomes 2, so here it is 2, oxygen becomes 6, so let me mention it as 3 here, right. So from the copper pyrite we are able to get Cu2S and FeS, from which FeS is oxidized to FeO. Now my idea is to extract the copper alone, not the iron. So the iron which is existing as an oxide has to be removed completely. So in order to remove that, what I must add is, I must add a flux. In order to remove it, I must add a flux. As soon as by the addition of a flux silicon dioxide, the FeO which is existing as a liquid will be cooled and solidified, will react with the flux and goes as ferrous silicate, FeSiO3. So the iron which is existing in the form of an oxide is completely removed right now. So that is what it is, here it is mentioned. The ferrous oxide formed by the melting reacts with the silicate to form ferrous silicate and it is completely removed as slag. Okay. Sir, in the very first reaction called roasting, the iron pyrite is completely oxidized, or it undergone a process called roasting, through which I am able to get the copper sulfide and iron sulfide, sir. Out of which the iron sulfide is completely converted into an oxide. It doesn't mean that there isn't any left over of ferrous sulfide. There might be possibility of existing of little bit ferrous sulfide which is not capable of undergoing oxidation. What are we going to do with it? We are going to see now. Right. As I have told you, Cu2S doesn't react with anything, so it just remains as it is. And I told you that not all the FeS will be oxidized to FeO and then removed as silicate. There will be some FeS left over, where in that particular moment that sulfides, that in the sense the Cu2S and FeS both remains as a mutually soluble with each other and forms a substance called copper matte or together mass, which is together of Cu2S and FeS combinedly called here as copper matte. And the copper matte which has been produced here will be separated because the copper, that metal of my idea, is present in this copper matte where it includes Cu2S. So it means I have to separate the copper. My idea is to separate copper, not the iron. I am not going to deal anything with the iron. Okay. Somehow we have found that only the copper matte has my metal. Okay. What I am going to do? The matte will be shifted into a converting furnace. It's called through the process called Basimerization process, through a converting furnace. Through that furnace, what is happening? If there is any leftover iron sulfide, will be oxidized to iron oxide. If there is any more ferrous sulfide, will be gets oxidized to iron oxide. Now, this iron oxide is further removed with the help of a flux SiO2 and removed as slag. Silicate, very easily I can easily remove it. So, hereby the leftover FeS is completely oxidized to FeO, and then FeO will react with SiO2 and removed as FeSiO3 completely. Now, the one that is left over is Cu2S. The one that is left over is Cu2S. What is happening here? Here, the Cu2S, it may be in the liquid or it may be in the solid, will be oxidized to Cu2O and sulfur dioxide will go out. Right, sulfur dioxide will go out here. To balance with, let me just write it as 2. Sulfur becomes 2, so it is 2. So oxygen becomes 3, so let me mention it as 3. It is not that all the Cu2S will be oxidized to Cu2O. There will be some Cu2S left it as it is. So, the leftover Cu2S, which might be in the liquid or in the solid, will react with the Cu2O that has been formed here. Cu2O, which is existing as a liquid or solid. Hereby, during this process, we are able to get a metallic copper completely. So, Cu as a solid with the evolution of a sulfur dioxide. Okay, to balance with, let me just make it as 2. So, copper becomes 6. So, here it is 6. So, thus I am able to separate a pure form of a metal over here. Right. See, you are able to find the evolution of a sulfur dioxide in the last step also. As soon as the evolution of a sulfur dioxide does completely, if the evolution is done completely, we will be able to get a solidified metallic copper. We will be able to get solidified metallic copper, which is called blistered copper. Okay, which is called blistered copper, very glowing appearance. So, it will be in the solidified mass. So, we call it as a blistered copper. So, this is a very important content for us in order to deal with the exam. So, make sure that you are very well aware of it. If you get any doubt, kindly let me know in the comment box below. Right. See, whatever we have seen till now, we have just witnessed theoretically with the help of a reaction. Sir said some furnace, he said some steel chamber and all, and he said bricks and all. How will I able to imagine it? How will I able to imagine it? Don't imagine. You will witness now. Right. Everybody over here are able to see a video over here. Here, this is a furnace in which the smelting process is carried out. Here, it is the steel chamber which has been constructed and around which bricks is placed. Why bricks is placed? Here, bricks is placed in order to prevent the loss of heat. Sir, what is actually happening there, sir? See, in this process, there are certain connectivity over which, this is a connectivity where hot air is passed into a furnace. Hot air of about 800 degrees Celsius is passed into a furnace. And we know that during the process, the impurities will be formed. Those impurities will be collected separately in the form of a slag when it is treated with gangue. See, I told you that gangue, when it is treated with flux, will get deposited as a slag very well, very clearly it will get deposited as a slag over there. Right. Since slag is collected separately, the left out copper sulfide and iron sulfide is completely transferred. Over here. Right. When the left out copper sulfide and iron sulfide is completely transferred here, it will deposit as a matte over here. As soon as the matte is formed, it will be completely converted into another furnace. Right. So I hope you are clear here. A steel chamber is placed around which fire bricks are placed in order to prevent the loss of heat. Hot air is passed of about 800 degrees Celsius. As soon as copper pyrite starts to ignite, it will give us FeO. That FeO will take up SiO2 and go as FeSiO3 as a slag. Then in the end, we will be able to find a mixture of copper sulfide and iron sulfide. Those two will be completely transferred into a separate chamber where a couple of copper sulfide and iron sulfide is collected as matte. We call it as a copper matte over there. Right. As soon as we have collected the copper matte, it will be transferred into another furnace. Right. So here this is a furnace properly which has been placed, over which the ore has been fed up. It has been heated. As it has been heated, the one which is molten liquefied will get settled down. Now, as I told, the copper matte has been formed here. Those copper matte will be transferred into a Basim converter here. As soon as it has been transferred into a Basim converter, what is actually happening here? We will be able to find it right now. As I have told, it has been placed at fire clay bricks. Okay, the copper matte is completely transferred into a Basim converter. What is happening here? If we are able to find any sort of an impurities like sulfur, arsenic and antimony, they are escaping completely as a volatile oxide so easily. Right. So as it escapes as a volatile oxide, the remaining which has been left out here is called the purest form of a copper that we are able to get here. Right. So this is what actually happening here. During the process also, we told that there is some FeS which is left over. Those FeS will be oxidized to FeO and then it will be removed as FeSiO3. Right. As soon as the evolution of copper sulfur dioxide goes completely, we will be able to get a 98% pure copper which is called as blister copper. Right. So this is what the blistered copper, and you are witnessing it in a solidified form right here. So the process that we have looked into is called smelting. Quite lengthy, but it will be very easier if you are able to understand it in a proper manner. Right. This is a long process. There are certain processes which can be done just like that. Not every ore. There are certain ores through which, through certain process, I can able to finish the reduction process just like that. In that, the first one is reduction by carbon. First, there is a condition that what type of a ore will undergo reduction with the help of a carbon. The ore which actually do not form carbide with carbon at its reduction temperature, which means I am carrying out a process called reduction at a particular temperature. At that temperature, if the ore doesn't form carbide with the help of a carbon, it can be reduced with the help of a carbon. If the ore forms carbide with carbon, I can't reduce it at its reduction temperature. I must opt some other way. Right. So this is a very important condition. Right. Metal which do not form carbide with carbon at its reduction temperature, only that can be reduced in this process. Right. What is actually doing it? The oxide ore will be mixed up with a coke, which is powdered charcoal. Okay, powdered charcoal. Here it is mentioned as a coke as powdered charcoal. Okay, and it has been heated in a blast furnace. Okay, what is happening? Let me take few examples over here. If zinc oxide, which is in the solidified form, if it is treated with carbon, which is in the solid, Carbon will take up the oxygen and goes as carbon monoxide in the form of a gas. The one which is left out is zinc there. So, zinc as a solid. Then you can also take Mn3O4 in the solidified form. If it is treated with carbon, carbon will take up all the oxygen and go as carbon monoxide. So, 4, here also it is 4, and the left out is 3 moles of manganese. Similarly, you can also use to reduce chromic oxide also, Cr2O3. If it is Cr2O3 which is in the solidified form, will be treated with the carbon which in the solid will be removed as a carbon monoxide, 3 moles to 3. Along with that, we will be getting 2 moles of chromium as a product. So, this is a process through which a reduction can be done with the help of a carbon. The next one, reduction by hydrogen. It does not mean that reduction can be done with the help of carbon alone. We can able to reduce a metal oxide with the help of a hydrogen also. How are we going to do it? See, if hydrogen is capable of reducing some other oxide, the metal which is present in the oxide should not be more electropositive than hydrogen. This is the condition. As we have witnessed for the carbon, for hydrogen also there is a condition. What condition is that? The metal oxide, it can be any metal oxide, but the metal present in the metal oxide should not be more electropositive than hydrogen. Okay, now we are able to find that hydrogen can reduce the metal oxide in which the metal is less electronegative than hydrogen. Right. Let me just take an example, silver oxide, Ag2O. If this Ag2O is treated with hydrogen, what is actually happening here? Hydrogen will take up the oxygen and go as H2O. Thereby, I am able to get 2 moles of metallic silver in the solidified form. So, this is an example. Right. If I am able to reduce the nickel oxide with the help of an hydrogen, I can't only rely on the hydrogen itself, for which I have to take up a mixture of an hydrogen and the carbon monoxide. We call it as a water gas. If I am able to reduce the nickel oxide, so when the nickel oxide that has to be reduced, if it has to be reduced by hydrogen, we have to take up in the form of a mixture, that the mixture must contain the hydrogen and the carbon monoxide together. We call it as a water gas. Right. So, hydrogen will be taken up, along with that carbon monoxide will be present. Thereby, what is happening here? Let me just take 2 moles. Carbon monoxide will take 1 oxygen and goes as carbon dioxide, and hydrogen will take 1 oxygen and go as water molecule. Thereby, I am able to find 2 moles of a nickel. So, 2 moles of a nickel will be separated so easily. Right. So, this is a reaction to show that hydrogen can reduce a metal oxide with the help of a carbon dioxide. So, a combination of hydrogen and the carbon monoxide is called as water gas. Then we will head into the next reduction process. This is also a quite important method, as I have told it for a smelting. A metal can be reduced by the metal also, which means a metal oxide can be reduced by a metal. What is the name of the process? The name of the process there is aluminothermic process. This aluminothermic process is widely used to reduce the oxide of a chromium with the help of an aluminium. Okay, chromic oxide can be reduced to chromium with the help of an aluminium. That is the main ideology behind this process. Okay, what I am going to take here, the metal oxide will be taken along with the powdered aluminium. Right, the metal oxide and the powdered aluminium will be taken, and it will be placed finely in a fire clay crucible. Right, the crucible which resists a greater temperature. That's called fire clay crucible. Right. Here, in order to begin this reaction, let me just specify you the reaction. Suppose if chromic oxide is reduced by aluminium, aluminium will take up the oxygen and go as Al2O3, and chromium will be deposited as chromium in the form of a metal. There it is. Right. In order to this reaction to occur, I need a greater amount of heat. How much of heat I require? I require 2400 degrees Celsius of heat. In the form of an energy, if I would say 852 kilojoule per mole of an energy. That energy can't be generated when a reaction is carried out between chromic oxide and aluminium itself. Okay, somehow I should manage in such a way that I should get that much amount of heat. I should generate 2400 degrees Celsius of an heat. So what I need to do? What I have to do is, I have to place a magnesium ribbon and barium oxide over these mixture, which means over these metal oxide and aluminum powder mixture, I have to place magnesium ribbon and barium peroxide. Right. So here it is. BaO2. What is happening here? Magnesium will take up the oxygen and goes as MgO, and barium peroxide will be turned into BaO, barium oxide. This reaction actually generates the required amount of energy in order to reaction to occur. So this is what actually happening here. This is a quite important reaction, so kindly make a note of it. Right. During this process, we may be able to find certain impurities. Those impurities can be removed through the process that we have witnessed earlier, also with the help of an active metal. Say for example, a metal oxide can be reduced to a metal with the help of an active metals like sodium, potassium, calcium, etc. So, let me just take B2O3, which is an oxide. This boron trioxide can be reduced with the help of an highly electropositive alkali metal, sodium 2. As I told, sodium will take up this oxygen and go as Na2O. Right. As Na2O deposits here, I have to balance it somehow. So boron goes here. So since it is a 3 oxygen, so let me just make it as 3. So sodium becomes 6, so I will make it as 6. Boron B here is 2, so it can be solidified. Separated so easily. Similarly, you can take Rb2O3, rubidium trioxide. This can be separated with the help of, this can be reduced with the help of magnesium to form MgO, magnesium oxide. So 3 magnesium will take up this 3 oxygen and go as 3 MgO. So rubidium will be deposited as 2 moles in the form of a solid. Also, you can use TiO2, titanium dioxide. With the help of a magnesium, I can able to reduce it. This magnesium will take up this oxygen and go as 2 MgO in the form of a solid. Right. So here it is 2. So titanium gets deposited as it is in the form of a solid. And thorium dioxide also can be used. THO2, which is existing in the form of a solid, can be reduced with the help of a calcium. So calcium will take up this oxygen and go as CaO. Right. So 2 moles. So let me mention it as 2. So thorium just deposit as it is. So these are other methods through which a metal oxide can be reduced by a metal also. The aluminothermic process that we have witnessed with the help of a theory, you will going to see right now experimentally. Right. See, this is a fire clay crucible. This is a fire clay crucible and which is placed in the sand. because that sand will prevent the loss of a heat. Here, the one which is green is a mixture of chromic oxide and aluminium, which is taken in the ratio of 1:3. Right. Here, the one which is black spotted contains barium peroxide and magnesium powder there. Now, this magnesium ribbon starts to ignite right now. As soon as the magnesium ribbon starts to ignite, it will react with barium peroxide and generates 2400 degrees Celsius. As that much amount of energy generates, we are able to separate chromium in the form of a molten state, and after cooling it, it gets solidified. So, this is what actually happening here. Right, with the help of a fire clay crucible. Then, the last part of the reduction is auto reduction. Auto reduction in the sense, I do not require any other metal or anything, just oxygen is enough, which means just a roasting process. There are some ore which on roasting will undergo a process called reduction, which results in the formation of a metal that I am going to extract. For such ore, reducing agent is not at all required. Reducing agent is not at all required. In exam, you will be questioned like, show that a reduction can be occurred without the presence of reducing agent in such a way. Right. So, we will witness a reaction. Cinnabar. When I say cinnabar, it is HGS. Okay, mercury sulfide. When this is heated with oxygen, it forms mercury acetate Hg with the evolution of a sulfur dioxide. So, this is what will happen. There it is. Right. So, this is a process which involves auto reduction where a roasting is taking place. Right. So, in this session, we have dealt widely in the process called reduction of metal oxide to a metal. To begin with, we have come to know that all the metal oxide can't be reduced to a metal with a single reducing agent. There are certain reducing agents which can reduce the metal oxide that entirely depends on the nature of ore. To begin with, we have started with smelting and reduction by carbon, followed by reduction by hydrogen, then aluminothermic process, which is called reduction of a metal oxide by a metal itself, and auto oxidation finally. So, almost 5 reduction process we have witnessed in this session. Right. In the next session, we are going to deal with the thermodynamic principles. So, if you are very comfortable with the channel and my class, kindly do subscribe, like, and if it is a good comment or anything, let us know in the comment box below. And don't forget to give a thumbs up for us. Right. So, this is Pranam Jaising signing off with today's session. Thank you.